This is a wafer made of silicon. A piece of silicon like this, whether doped or undoped, is not very useful. A more useful device can be formed when we put p-type and n-type silicon next to each other, forming a p-n junction. Such device is also called a diode. On a piece of wafer, the 3D schematics and 2D sideways cross-sections of a p-n junction is shown here. There are many devices like this on one wafer, which is usually diced into smaller pieces before being packaged for sales on the market. We shall first study the static characteristics of a p-n junction before battery is connected to it. In particular, we shall look at the carrier statistics and band diagram at different locations of the junction. Recall what you have learned from the study of doped silicon. An electron from a donor moves around the silicon. When it moves to a location with a hole from an acceptor, it may take its place by recombination. When the process is complete and reach equilibrium, the location of donor carries a small positive voltage, and the location of the acceptor carries a small negative voltage. Let's start with a piece of intrinsic silicon, and we add acceptors to the left and donors to the right, as shown in the picture. Right after the dopants are added, the excess electrons and holes initially stayed with their parent atoms, and the whole system is neutral. As there are more electrons on the right, these electrons diffuse to the left. When an electron sees a hole, recombination may take place. After recombination, the hole and electron disappear. The donor becomes positively charged after giving away an electron, and the acceptor becomes negatively charged after giving away a hole. We also assume that recombination takes place in an orderly manner, that electrons at the nearest column to the junction migrate to the p side and recombine first, before the second column of electron takes action. And recombination takes place at the column closest to the junction on the p side until all holes at that column are recombined before recombination would take place at the second column. In the process, carriers near the junction are depleted and a depletion region is formed. The covalent bonds in the depletion region are similar to those in intrinsic silicon, and the depletion region is generally assumed to have no carrier. However, this is not exactly correct, because some carriers are always there, as in intrinsic silicon. But the number of carriers in the depletion region is much smaller than the number of those added by dopants, and these carriers are usually ignored. As the process of carrier diffusion continues, the depletion region expands, and more charges are accumulated. The accumulated charges tend to oppose further diffusion across the junction. To visualize the detail, let's follow the forces experienced by an electron moving across the junction. When it is on the n side outside the depletion region, it experiences no net force as the charges on its left balance out. When it diffuses to the depletion region, the positive charge to its right tries to pull it back, while the net negative charge to its left also pushing it back. As the depletion region expands, electrons have to overcome larger forces over a longer distance before it can find a hole to recombine. Therefore, the diffusion process will eventually stop, and an equilibrium is reached with a particular depletion width. To further study the properties of p-n junction, some simplifications are made. The first one is the abrupt junction approximation. It assumes that there is a clear boundary between the p-type and n-type silicon. In reality, there is a transition region where both donors and acceptors coexist. The second one is the depletion approximation. It assumes that all carriers in the depletion region are depleted, and there is a clear boundary between the depletion and neutral regions. With these two approximations, we can simplify the representation of p-n junction into a solid divided into different regions as shown here. In this picture, there is a clear boundary between the p-type and n-type material. The depletion region on the N side carries positive charges, while the depletion region on the P side carries negative charges. After the depletion region, it is the neutral regions where the silicon retains the carriers introduced by the dopant.